Hello, everyone. My name is Sharon White. Welcome to today's webinar on HLS. What is it and when do you use it? This is a 1-hour webinar from 2 to 3 Eastern today. We'll have a lecture, a demo, and then conclude with Q&A. We do encourage questions, so please use the chat panel to ask questions throughout today's training, and we will get to them at the end. Today's webinar is being recorded, and once we're done, we will send the recording out to everyone. Before we get started, let me introduce to you BLT and our team. BLT has been in the design services business for over 30 years. We were started by one of the original Xilinx FAEs. We have our headquarters here in Maryland, and we have a brand new office in Melbourne, Florida that should be ready in a month or two. We design chips, boards, software, and complete systems for commercial, military, and intelligence clients. Our designs are in space, undersea, and everywhere in between. And we've been teaching Xilinx, or now AMD Xilinx, training for 25 years. We're an AMD Xilinx certified alliance member and authorized training provider. First, I'd like to introduce you to Lisa Weaver. Lisa is our senior strategic accounts manager, and she's your go-to for questions for training and design services. Lisa is on today, so if you have any questions, feel free to message her in the chat panel, and I'll put her contact information in there for you as well. Now I'd like to introduce Colton Fidel. Colton is a project engineer at BLT on digital design with FPGAs and embedded systems, specifically MPSOCs for both commercial and defense applications. In his 7-year career, he has designed tools for electricians, flight control systems, for tilt-rotor aircraft, flight line test equipment, electronic warfare simulators, and SAR-based satellites. He's definitely ready for spring to get here. Colton likes to garden and care for his houseplants in his free time. So welcome, Colton. Colton, you're on mute.
Oh, sorry. Thanks, Sharon.
Sure.
Yeah, really excited to get to my gardening this year. It's finally getting warm out, so that'll be fun. But yeah, we have a lot of information to cover today. Like Sharon mentioned, we're going to go through an introduction to high-level synthesis. We'll start with what it is in a broad sense, and then look at the tools AMD Xilinx provides to perform high-level synthesis, specifically for their silicon parts. Then we'll have a live HLS, Vitis HLS demo. So I'll walk you through creating a project, simulating it, synthesizing it, and exporting the RTL that gets generated by it. And then we'll have a Q&A session at the end. All right, so let's start with an introduction to high-level synthesis. So for those of you that may not know what exactly high-level synthesis is, maybe you just heard of it in passing, it's essentially a tool or process that allows developers to turn C or C++ code or other high-level languages, programming languages, into actual RTL hardware. So you no longer have to write Verilog or VHDL or system Verilog in order to create netlists and bit streams that target FPGA devices. You can now use C and C++ code and create modules that you can then use to build an entire bit stream up. So HLS is just the process of turning C or C++ code down into a lower level RTL language. So the synthesis process is really not too much different than synthesizing C code for other hardware targets. So in your existing code, you may have some C, a code that gets turned into machine code that can then run on a DSP processor, or some GPU graphics card, NVIDIA graphics card, or even a standard Intel or AMD processor as well. And now with HLS, you're able to turn that C code into code that can then target FPGA devices. So really, it's just in that synthesis compilation process that the differences exist there. And similarly to these other targets, when you're targeting an FPGA, there's some stuff you can do to the code that specializes it for that target. And with HLS, that's generally called directives or pragmas, and that's things You're going to add to the existing C code that tell the tool how to create the hardware that you want. So we'll look at that a little bit later today. All right, so high-level synthesis, again, it allows FPGA users to write specifications or algorithms in higher-level languages like C, C++, or OpenCL, and create RTL and hardware netlists from that. So it also allows software developers to target FPGA devices now and take advantage of all those things you get when you use an FPGA. So the massively parallel architecture, the increased performance, and better cost and power utilization over traditional processors. So this is sort of what the overall flow looks like. You'll start with some C code, higher level software code, and you can use a bunch of different libraries. So AMD Xilinx provides a lot of libraries that have code that has been customized to efficiently target hardware. And we'll briefly look at some of those libraries today. And then once you have your C code, you'll run it through the Vitis HLS tool, which will output your Verilog or VHDL IP that can then be brought into IP catalogs for other AMD Xilinx software tools. So that could include Vivado or Model Composer, so using MATLAB and Simulink with Model Composer. So you can bring all those cores that you create in HLS and bring them into the other AMD tools, AMD Xilinx tools, to then create an actual FPGA bit stream from there. So taking it in a step-by-step process, the first step is to write your C code or C++ code. And once that's finished, you'll run a C simulation. So as if you were running or creating a test bench for any other C code you've written before, you'll still write a similar C test bench and use that to verify the correctness or functionality of the C code that you've written. So here you're just verifying that your algorithm works as intended. And then once you've verified that your algorithms in C work correctly, then you can run through C synthesis. And that's what the HLS tool is going to use to actually create the hardware. So we'll look at that in more detail later today. We'll see how it actually turns your C code into hardware. So there's a few phases or steps that it takes to go and do that. And then once you've generated your RTL code, the Vitis HLS tool provides this feature called cosimulation, RTL cosimulation. So it's going to take the results from synthesis, use the input data vectors from your C simulation file, run them through these RTL adapters, and then it's actually going to test the HDL code that was generated with the input data from your C simulation. And then it will capture the outputs from that RTL code and create output vectors, and then compare the output of the RTL code to the expected output from the C simulation. So it's going to actually use that same simulation file, test your RTL code, and from there, you're going to be able to be confident that the RTL code that was generated is going to perform and create the exact results that your C algorithm expected. So using this flow, you no longer have to create VHDL test benches, which can be a very time-consuming process. You can rely solely on your C simulation test bench for this module. It's still definitely a good idea to create a higher level test bench in System Verilog. So once you start connecting up these cores that you're creating with HLS into a larger bit stream, you'll still want to create a top level system simulation. But for module level simulations, you can rely on this existing C simulation file, and you gain a lot of productivity benefits there from doing that. Then once you've verified the RTL works as expected, you can package that RTL up and import it into some of the other tools that AMD Xilinx provides. to further finish and create your top level design, right? So HLS is generally just used for modules, individual IP cores. It's not useful for creating an entire bit stream there, right? You're going to want to create individual IP cores constrained to a single clock domain, and then use those cores that you've created as building blocks for a larger design. So you'll still need some sort of wrapper VHDL file, or using Vivato IP integrator to start piecing together those IP cores that you created. So that was a look at what HLS is, kind of at a high level. Now we'll look at some of the reasons why you might want to use Vitis HLS. So if you've ever done software programming and some hardware development as well, you'll understand that there's somewhat of a productivity gap between the two domains. Software development is generally seen as a much more rapid domain there, and hardware is a little bit slower. Here it says it's analogous to assembly code programming. So you're really working at the lowest levels, piecing together registers, piecing together lookup tables and flip-flops. So it's pretty analogous to if you were working in the lowest level programming languages, so assembly code there. So HLS is trying to bridge that gap and make hardware programming more productive and more rapid. So the HLS tool will provide benefits not only to hardware designers, but also software designers as well. So for hardware engineers, they can now work at a higher level of abstraction. So they no longer have to code in VHDL and Verilog. They can write in C code, which is much more efficient and rapid versus VHDL and Verilog. And for software designers, they can take their computationally intensive parts of their code and algorithms, and instead of targeting processors or DSP chips, they can target specified hardware or custom hardware by using an FPGA. So they can gain the performance benefits of using FPGAs now. So it's not only useful for hardware engineers, it can be useful for software engineers as well. But having said all that, there is a steep learning curve. So you'll notice as we start going through some more of the technical details, there's a lot of information there and a lot of stuff you have to learn to get good at creating HLS modules. So HLS leverages the unique tools developed by AMD Xilinx, and that includes the Vitis HLS tool and Vivato. So overall, once you conquer this steep learning curve and continue to use Vitis HLS, you can see up to a 15x productivity gain over a typical HDL flow. So this is for hardware designers here. So comparing RTL to C-based design, you'll see in traditional RTL coding, not much of the time is spent in design. Most of the time is spent in synthesis, place and route, and verification closure. Maybe only 20% of the time you're actually writing your VHDL or Verilog hardware. And the rest of the time is spent making it work. And comparing that to a C-based design, a majority of the time you're spending here in the development of your C code. And then kind of following through that, the system integration and implementation is kind of handled for you by the HLS tool and the Vivato IPI integrator. So now most of the time you'll be spending actually developing your code and less in that synthesis, place and route verification time, because that's all handled for you by the Vitis HLS tool. So here's some estimates of the productivity gains you'll see by using HLS. Up to 40x faster for any derivative design. And this is just looking at it in a different kind of graphical setting here. So you have your VHDL code here, which may be up to 100,000 lines if you're using VHDL Verilog, or 50,000 lines if you're using System Verilog or VHDL 2008. But this is just the general flow here. You're going to do some module level simulation here, but a lot of times you'll spend most of your time debugging on hardware, which then comes back to the VHDL Verilog and updating that code, which is a timely process. Updating C code is much more rapid, and running through C simulations much more rapid there. So an equivalent C design may only, or C++ design may only have 5,000 lines of code. And you'll finish the design closure much faster in a C environment with C test benches. So it's just a much more rapid iterative process here versus doing it in Verilog. In one study that AMD Xilinx did, they seen the traditional flow could take up to 240 people months. But if they had used an HLS-based flow for a very similar design, it would only take 16 people months for a very similar type of design there. So coupling HLS with the Vivado IP integrator to piece together all those blocks just leads to a much quicker flow overall. So C-based fast iterations, easy exploration using the pragmas and directives to specify what type of hardware you want to target there. RTL, much slower. Exploration is difficult. To change different hardware aspects you're targeting, you have to rewrite a lot of VHDL or Verilog code. But in C-based design, you're just changing some pragmas or directives there, which are just kind of settings you're applying to the C code to tell it what hardware to target. And for verification productivity, in a C-based design, you're doing most of your simulation in C to verify the algorithms you've created. Compared to RTL, simulation is very slow there. So most of your simulations in a C-based design using HLS, you're going to be simulating using a C test bench. And then maybe you'll run the cosimulation once at the end, but you've verified a majority of your algorithms just using a C test bench there. So the simulation time you gain is also a lot of productivity gain there. So now let's look at HLS kind of under the hood. What's happening under the hood? So in order to turn your C code into RTL, there's sort of three phases that the HLS tool will perform. That's scheduling tasks, binding them to hardware, and then creating any state machines that are needed to loop through that logic. So the scheduling phase is going to look at the clock frequency that you're targeting. It's going to look at all the operations that are in your algorithm or your C code, and then it's going to schedule those operations kind of on a horizontal timeline of clock cycles. So it's going to say, this is the clock frequency I'm targeting. These are the operations I have. How many of these operations can I fit in each clock cycle? That's essentially what it's going to do there. And you can use directives or pragmas again to, so if this was a loop, you could pipeline it. So, on this clock, it may be doing A times X plus B. And on the next clock, it's going to take the result of that, add it to C. But it could also, on this clock, then start beginning to compute the next value for these inputs. So if new inputs are available, it could start here. So that's kind of what pipelining would be. So scheduling, it's majority of it is determined based off of the clock period. So what's the clock frequency you're targeting? But some of it also depends on the device you're targeting. So what operations or what resources are available there. And it's going to be able to determine how many operations it can fit in a single clock cycle. So if it can fit all the operations in one clock cycle, then then you're going to be able to accept new data on every input. There's not going to need to be any control logic necessarily. But if your clock period or frequency is too high, then it's going to have to start scheduling these tasks over multiple clock cycles. Once everything's scheduled, then it will actually bind those operations and memories to hardware resources. So here in this example, we have a simple function that's going to multiply two inputs and then add two values to that result and return it. So in the scheduling phase, it determines that there's basically three operations here, the multiply and two additions. And based off of the targeted frequency in the device, it's going to say I can fit a multiply and add in one clock cycle. I have to register that output, and then I can perform the second addition in the next clock cycle. Then in the binding phase, it's going to look at those operations. The initial binding phase sees a multiplication, an addition, and then another addition. And then the target binding phase is going to look at the resources from the device selected and place these resources place these operations into a single resource. So the multiply add can fit in a DSP slice, so it'll place them there. And then this last add could be placed in either a DSP slice or just use general logic to perform that addition. So using directives, you could tell the tool to use a DSP slice for this, but it's saying I can perform this addition just using general resources and fit it in this clock cycle. So that's what I'm going to do there. And it will also bind these inputs, so your function level inputs to IO ports. So depending again on the data type and what pragmas or directives you've applied to that, your input and output ports will have certain signals and handshaking signals associated with them. So the control logic extraction phase will look at the code and determine if it needs to create a finite state machine to handle the data flowing through the design. In the previous example, there was no control logic extraction, and that's because there were no loops. So it didn't need to have any memory over anything there. In this example here, it's the same arithmetic, but now it's looping through an input array. So this is some memory element. It's going to loop over 3 times, perform the same arithmetic on all 3 values in that array, and then output and store them in some separate array there. So now since it's looping through this code, unless you unroll it, so by default loops are kept rolled, which means it's going to follow sort of a C based sequential execution here. It's going to execute this loop for the first iteration of the loop, then it's going to execute the second iteration of the loop and the third iteration, and it's going to reuse all these hardware resources for each iteration of that loop. Now loops in VHDL or RTL are generally unrolled, so it's going to create copies of that. But by default, HLS is going to keep these rolled, use the same resources, and just iterate through that. So that's why there's some control logic needed to determine what count of the loop you're on, keep memory of that, and feed in the new inputs to those operations. Right, so since there was an array in the top level function, that implies some sort of RAM. By default, it's going to use block RAM. But again, by using pragmas or directives, you can tell the tool to use FIFOs, distributed RAM, or individual registers. So you can see how using HLS allows you to change your hardware pretty drastically just by changing a simple setting in the code. Whereas if you were changing, from block RAM to use a FIFO or individual registers in VHDL code, that could require a lot of recoding in your design. So back to the control logic. The HLS tool will recognize that this addition of B and C happens only once, or only needs to happen once, right? It's the same for every iteration of the loop. The result of this is the same. So it's going to pull that operation outside of the loop, right? So the loop is C1, C2, C3. It's going to pull it outside the loop, perform it once, and kind of register it and store it there for the rest of the iterations of the loop. But since your X value is changing for each iteration of the loop, That's why this control structure exists now. So in state C0, it's performing this addition. Then it's entering the loop in C1. In C1, it's going to update the loop counter, and it's also going to update the address that it needs to read this X value from memory and issue that read command. C2, it's waiting for the data to come back. So whatever the latency of this RAM element is going to be accounted for in C2. And then in C3, it gets the value back from RAM, performs that final multiplication and addition, and then issues the write command out to the other memory element that stores the result of that. So then it will loop back to C1, update the loop counter, increment the address, and perform it again. So it'll keep performing the C1, 2, and 3 over and over again until you get your final data out. So here's some terminology that's important when analyzing HLS designs. One of them is latency. So that's the number of clock cycles required for the function to go from input to output. So in this example here, the functional latency is 10. 1 for that initial state of calculating B and C. And then you have the 3 states iterated 3 times, and that's 9 additional clock cycles before you complete the function call. So one call to this function will take 10 clock cycles of latency for this entire, for this design. Initiation interval is often very important as well, and that's the number of clock cycles before the function can accept new input data. So in this example here, since the loop was left rolled and there's no pipelining applied, the initiation interval is the same as the latency. You have to wait for this entire function call to complete before you can begin processing a new array of input data. Right? So this input 0 input array of depth 3 there. You have to wait till it's all completed, and then you can update the function with new values for B, C, and the input array. So now let's look at how the HLS tool converts C to RTL. It's dependent on what types of code you have in there. So your top level function, other C functions, loops, and arrays will all get synthesized differently. Top level functions will get turned into your top level functions inputs and output arguments get turned into your IO ports for your RTL code. And again, depending on the pragmas used, you can get different handshaking signals there with them. Other C functions, so not your top level function, will get turned into sub-level RTL blocks. So here you have function C and D, which are sub-functions for your foo top. And those IO interfaces get abstracted away from you. Loops we just looked at are kept rolled and pipelined by default to improve performance. And arrays will get turned into some sort of memory resource. So that could be block RAM, distributed RAM, ultra RAM, or even individual registers or FIFOs. Now let's look at the HLS support. In general, most C and C++ constructs are supported. So all the native data types are supported, fixed point, floating point, those are all supported. And the HLS tool supports a complete bit accurate validation of the C model. So you can have arbitrarily defined bit widths data types as well. There is comprehensive library support. So we'll quickly look at some of the libraries that AMD Xilinx provides to create more efficient and optimized hardware. One is the arbitrary precision data type library. So that allows you to create data types that aren't on the native C data type boundaries. So you can have a 12-bit data type, 13-bit data type, however many bits you need, you can use this library to create data types of that bit width. And simulation support exists for this as well. The HLS math library is pretty much a copy of the C math libraries, but it's been optimized to target hardware. So in general, if you are using a C math library for some of your algorithms, you should instead use this HLS math library. And it has pretty much support for all the C math functions, but you will want to go and look in there to make sure your functions are supported. There's a HLS streaming library, and this helps you to model streaming interfaces. So you will have to use a C++ code for this, and there's a template class called this HLS stream class here. And that just allows you to model streaming interfaces. Then there's the Vision library. So this contains a lot of classes and functions that are useful for analyzing video data or processing images. And then there's some IP libraries. So these just allow you to instance and target Xilinx IP blocks. So in Vivado, there's an FFT IP core, a FIR compiler IP core. So using these libraries will allow you to target those IP cores and just implement these algorithms very efficiently. Some constructs aren't supported. So there's a few of them here, and we'll cover them individually. System calls are not supported. HLS cannot synthesize them. So any call to the operating system, whether that is a printout, so a printf, fprintf, anything involving time, so any sleep function or time or getC, none of those will work since they all make calls to the operating system. Those are not synthesizable. Dynamic memory usage is not supported. So you can't use malloc, alloc, or free. You have to define your memory resources ahead of time so the synthesizer knows how much block RAM to create or how much memory to create in hardware. Or declared types and recursive types are not supported. Pointer casting is supported, but only between the native C and C++ types. You can't have general pointer casting so in your code. You can have pointer arrays, but the each pointer has to point to a scalar or an array of scalar. You can't have an array of pointers that point to other pointers. And function pointers are not supported at this time. And all this information is in the HLS user guide. So this is kind of like a quick rundown, but definitely reference the HLS user guide when creating any code, just to make sure that your code, or importing any code, just to make sure everything you have in there is supported. If you have a system call in your code and you try to run through synthesis, the tool is just going to error out, and it will, it'll tell you in the error message exactly why it's failed. Once your code's written, then you'll determine or create your top level function. So in C programs, your top level function is usually called main. In Vitis HLS, you can actually select any subfunction to be your top level function. And that's just telling the tool what function you want to synthesize. And that's important because those input and output arguments for that top level function are going to get turned into the input output ports of the resulting IP core that gets created. So here is just giving an example of if you want to synthesize both function A and B, the only way to do that is to combine those two functions into a single higher level function, since you can only have one top level function for an HLS project. You could just create two separate projects and create an IP core for function A and function B, and then manually make the connections. But you could also just create a wrapper for them. So this function AB just makes a call to function A and B. And now you can choose this function AB as your top level function. So now looking at the tool a little bit, when I demo the Vitis HLS tool, you'll see this. This is the flow navigator, and this is where you can run all the different steps of HLS. So you have quick access to running the simulation, synthesis, viewing all the reports from synthesis, CRTL cosimulation, viewing all the reports and output from that, and then implementation, which is really just exporting your RTL here. You can also run implementation, but the results you'll get from that aren't going to be too useful, right? So in HLS, you're just creating a single IP core. Running implementation gives you better results once you start connecting everything together. And you'll generally have a good idea of if you're going to meet timing here from the synthesis results. So the synthesis results will tell you how you're doing on timing. Implementation could give you a better look at that because it will actually place them on the part. But again, it's not too meaningful until you start connecting it to everything else in the design. And once you have run through synthesis, you have these tools here that allow you to analyze the results. So there's a schedule viewer, function call viewer, data flow viewer, and timeline trace viewer. So these are just different tools within the Vitis HLS software. In the schedule viewer, you'll be able to see in a nice graphical setting how the different loops and subfunctions of your code are getting called and dependencies between them. So you'll see an overall timeline with number of clock cycles here. And then you'll see kind of green boxes that are tied to different loops or function calls. And you can double click these boxes to see a similar schedule viewer, but for individual operations inside of these functions or loops. So this is just showing you dependencies between your code functions and overall timeline of how long it takes your code to execute. In the function call graph viewer, it's kind of displaying the same information, but in a condensed, more vertical top-down flow instead of a horizontal timeline flow. So here you see dependencies kind of pointing over with these green arrows to other function calls. You can see the parallelism in your code, right? So all these functions here that are horizontal kind of can happen in parallel. And you'll see the initiation interval and latency of each of these tools as well. Yes, I'll show you where to open all these when I get to the demo portion. Yeah, so now inline functions are no longer visible. They'll be kind of cascaded up into total blocks here. But this is nice to see what parts of your code, what functions are kind of stalling or creating bottlenecks in the design. And for an even quicker view, you can create heat maps in the function call viewer, and that will show you, the functions or loops or sections of code with the worst latency and initiation intervals. So in general, your performance is going to be limited by the worst performing subfunction or loop in here. And then you also have the data flow viewer. So this is, again, another way of analyzing your code. But here now you get to see the channels that are created between subfunctions in your code. So here in this example, you have a read data function, a calculation function, and write data. You can see how the data is being passed between them. So you can inspect any of the FIFOs or ping pong buffers here that are used to create the channels that pass data between all the subfunctions. And lastly, you have a timeline trace viewer. So this is actually going to show the results from your CRTL co-simulation. So it's going to show you how long the code spent in each your subfunction here and how many calls to each subfunction there were. So again, you can identify a parallelism here, dependencies, and just see the co-simulation results in an easy view. You can also view the co-simulation results in the RTL simulator. So I'll show that as well. There's a way you can open up XSim or your other targeted RTL simulators and view the waveforms there. All right, so now I'll quickly go through a live demo. So I think we're going to hold some of these questions. There's a lot of questions coming in. I think we're going to hold off on answering them until I finish this demo and some closing remarks. Yeah, I just wanted to quickly show the Vitis HLS tool. So when you open up Vitis HLS, you'll be prompted with this welcome page. And here you can do some generic things, create a project, open existing project, get some examples from AMD Xilinx's repo, GitHub repo, there's examples there, and also has links to the user guide, some tutorials and release notes as well. So I'll create a new project. Give it a location. Then it's going to prompt you to add any design files. So here you just have to add your C code. You don't have to add the header files if they're in the same directory. It'll automatically find them. But if they live in some other directory, you'll want to manually add those. Then once you've added your C code, you could choose your top level function. So this is what's going to determine your input outputs to the generated module here. And there's options for simulation flags as well. And then it will prompt you for your test bench files. So I'm going to add my test bench files, my input data file and my expected output data files. Then we'll ask you for a solution name, clock period, so what frequency you're targeting, and the device. We're going to target the CCU 104 for this example. And clock uncertainty is just the uncertainty you're telling the tool to use or allocate for kind of routing resources there. So then the HLS tool opens. You have your general toolbar with some things you can open here. The user guide, runs through all of these. I won't go through all these individually, but you'll see that a lot of the libraries are automatically included for you. Here's that header file. You can see it was found automatically. And then my source files, I have my dct.c. So this example is performing a discrete cosine transformation of some input vector here. And this is an algorithm that's generally used for compressing files. So it's an algorithm used in image compression for JPEG images. Then you'll see all your test bench files. So in the test bench, it opens the input data file, opens the output data file, and then it will call the function with that input data file and output data file to write to. And it will compare the output results to the output golden data file. So this be expected array. So once you've added your code and run through, or once you've added your code and your test bench, you can run simulation. There's options to launch debugger. So that's like a typical GDB debugger. You could step through your code, see what's happening. You can add input arguments there as well. So then you'll see the simulation running. And you see the output here. So this is the output that was in that code and the test bench code. Results are good. So it compared all the output values to the expected output and they all matched. So it said results were good there. So we verified the functionality of this algorithm. Now we can run C synthesis. Again, we're going to give it a clock period to target, board, and uncertainty. And we'll use just the Vivado IP target flow. This is going to create RTL for Vivado. So you'll see the output. You can see the output VHDL and Verilog code after this step. And here's the synthesis results. So you'll see the targeted clock rate, the estimated rate. So based off of the scheduling phases, binding phases, it will tell you what how much time it needed to complete all those operations. So in a single clock cycle, it never needed more than 3.59 nanoseconds to complete all the operations. So you could actually target a much lower rate here. You could double the clock rate and still probably meet timing there. So if timing wasn't met, this would flag as red, and you'll then definitely want to go look through some of these reports and function call graph viewer. So that's where you can access some of these different views here. And you'll want to run through all that if you notice that your estimates are not meeting the performance that you are targeting there. You can kind of dissect it and see why. You can also see the interfaces that are created. So here's your input and output ports. It turned it into block RAM. So you have your address, chip enable, and data lines for the input and the output memories there. So as you start changing around different pragmas, you can see some of these signals changing. And those, again, are your input output signals to the RTL module that gets created. And you can see the resources used. So this is how many DSP slices are being used by each loop or function. And you can, again, also see how much BRAM is being used as well. Then you want to run through cosimulation. So now this is going to take the outputs or take the synthesized results, run the C simulation code, data input vectors through it, and compare the output vectors to the expected output. And you could target different simulators. And if you use this dump trace signal, then you're able to see the wave debug. So now this will actually open up XSIM and show you the waveforms for the actual hardware. So it's kind of nice that this flow navigator kind of has everything in a sequential manner. In general, this is the flow you're going to want to follow. Simulate it, synthesize it, run co-simulation, and then implementation. And at each step, there's reports and viewers that you could call to help debug your code. So now it's actually opening up Vivado to show you the XSIM waveforms. Here you can see your input and output signals. So you see on the input side, there is this memory input. So it's reading from this BRAM element, and here's the read back data that's getting fed into the design. And then once it's computed everything it needs to compute, then it writes it back out. So you see the output port, separate BRAM interface, writing the data out. The write enable goes high, the chip enable goes high, and the address will increment for each data piece that's being written out. You can add any sub-level signals in here too, but the generated Verilog and VHDL code is pretty hard to read and hard to follow through, so it may or may not be useful, but definitely those function level signals are very easy to use. Then once you've passed cosimulation, oh, I meant to show you guys there. So cosim, we'll use that same C test bench and have the same printout. So you see results are good. It matched the C simulation expected results as it passed it through hardware. Then you want to export your RTL, choose a location. You can add constraints files, and you can also set the IP configuration settings as well here. I'll just leave them as the defaults. And you'll always be able to see everything happening in this console menu. So it'll keep you updated on what's going on behind the scenes. Here's the man pages. This is finished exporting the RTL implementation. So you can see this zip file now, and has constraints, documentation, and the HDL. You'll see your actual HDL files here. So you can see there's a lot of code that gets generated. A lot of it's not very readable, but you can again, add any settings or add any of these signals inside these individual HDL files to that waveform viewer to kind of see what's happening there. And that's pretty much it. So then you can take this exported HDL and bring that into Vivado and build larger designs using this kind of block as a building piece. So that's pretty much everything I wanted to demo there. Yeah, so we can go into our Q&A session now. I see Ellie is answering some questions. Someone just asked what the run implementation is for. So this will actually place the design on an FPGA and kind of generate like a simple bit stream. So it's going to use just a bunch of basics and IO buffers to create a kind of pseudo bit stream, but it's just going to place it and give you a better idea of the timing. So the report from synthesis timing isn't super accurate, right? So it's not accounting for any routing delays. Those are just estimated by this uncertainty. As you run implementation, it will get a better understanding of the routing delays that's needed, but it's still not going to be able to, you won't have full confidence in that until you start connecting this exported IP core to the rest of your design and run through implementation there. Yes, in C++ you can define custom classes. Those will get, depending on where they're used, if they're used at a top level function argument, they're going to get turned into IO ports, right? And each element in that class is going to have its own IO port. But if it's just used inside of inside the function internally or sub-functions, then it'll just get turned into HDL equivalent of if it wasn't a class. It's not going to, it's not going to create, the memory structure that you would expect in C++. Oh, sorry. Yes, someone asked if you're using C++, can you use classes? Can you create custom defined classes? So yes, you can. And then they asked, how are they converted to HDL? And they're converted to HDL the same way all other variables are. But the special case there is if they're used as top level function arguments, they'll be broken down. Each element of that class will be broken down into an individual input and output argument. So another question was, what are the differences between what are the differences and advantages of using the Vitis video library over the HLS video.h library? For that one, I believe the Vitis video library is just a improved version, so it's been rewritten. All the same functions should exist, but it's better optimized now and will more efficiently target the hardware. So just kind of under the hood stuff, benefits there. Another question was, what kind or type of algorithms and designs are best suited for using HLS, and which are the worst? So HLS really thrives when you are using it to create modules that are some specific mathematical equation, right? So some specific mathematical algorithm. So some examples of that would be filter algorithms, either for RF signals, RF data, or video imaging processing, any type of filters or DSP algorithms. That's really where HLS thrives. So, with those arbitrary precision data point libraries, you can perform math in just a few lines of C code, where that might have taken hundreds of lines of Verilog or VHDL code. So that's really where HLS is best suited. It's not suited well for complex state machines. So if you have some kind of complex state machine with a lot of nested conditionals and jumping around, HLS will not generate great code from that. It'll quickly explode in resource utilization there. So try and stick to using it for mathematical operations. We have some streaming interface, or you're processing a frame of data. So some 2D array of data. That's where HLS works the best. And someone asked, can you use existing software code in an HLS design? Yes, you can, with some caveats. So again, when we covered some of those unsupported constructs, you can't do your system calls, recursive functions or recursive data types are not well supported. Pointers to pointers aren't supported. So you got to make sure that your existing code isn't using any of those unsupported constructs. And you'll want to optimize or maybe restructure the code a little bit to one, have these sort of labels in the code. So you're going to want to start labeling your loops. And that's just, it helps you when you get to the schedule viewer or function call viewer. Those labels directly correspond to kind of the outputs that you get to see here. So make sure you're not using any unsupported constructs. Start labeling your code. And from there, yeah, you can start running through synthesis. You're probably not going to get exactly what you want the first time you run through synthesis there. From there, you're then going to want to start applying some directives to all these loops and your top level function inputs and outputs. So here's a kind of a tab where you can start applying directives there. So I can insert directives on these input and output arguments. So here's a list of kind of all the directives I can apply there. And the HLS user guide will kind of go through what all these different directives mean. And our HLS course also goes into a lot more detail about using directives and how you can optimize for throughput, optimize for latency, performance, and those sorts of things, and resource utilization. Yes, the HLS does have a predefined method for Axie4 streaming interfaces. So you can specify that as a streaming interface here with directives, and that will create certain things for you, but you will definitely want to use the HLS stream class for any inputs to your top level argument that are going to use Axie4 streaming interfaces. And someone else asked how this compares to other approaches like Simulink or HDL Coder. So they're similar, definitely. Our Model Composer course actually goes through comparing those two in some detail. The main difference you'll see is that with HLS, you get to directly control the hardware that's created with all these pragmas and directives. With Simulink and HDL Coder, you don't get that granularity in what you're producing there. And it also has, built-in simulation features and this co-simulation feature. So it's kind of bringing all these components together in one useful, one convenient, software application. Someone asked, do we have complete visibility into the RTL produced? And yes, you do. So again, in this, once you export the hardware, you can go into these folders here and look at the actual HDL that gets produced. I mean, you'll see that it's not exactly the most readable code. Some of the signal names aren't the greatest, right? So this is just pointing to, this signal just points to a line of code. So it can be pretty difficult to read, and there's basically a process for every single signal. So very difficult to read, no comments. So you do have visibility into the RTL produced, but I wouldn't say it's very useful for anything. Really, you're going to do all the debugging through the summary report results and these different viewer tools as well. And you can always create a new solution. So all of these synthesis results and reports are tied to solution one. You can always create a second solution and then compare results between solutions.
All right, so I want people to be able to keep putting questions in. We're almost 10 minutes over, so I just wanted to let everyone know it's already 3 o'clock. If you have questions, please go ahead and put them in the chat panel, and I'm just going to interrupt Colton for just a minute because I wanted to reiterate that we do have some HLS training opportunities coming up. I put the links into the chat panel already for the high-level synthesis with the Vitis HLS tool. That's on April 11th. It's a 2-day class, and we also have the Vitis Model Composer, a MATLAB and Simulink-based product. It's a 3-day course, and that's on April 4th. So those are already in the chat panel for you. We also have no cost opportunities coming up for you. So we've got a 4-hour no cost workshop on advanced debugging. That's April 19th. And our next webinar in May is on verification of SOC designs. I will put those links into the chat panel for you in just a minute. And we just had a question about in-person training. So this is great because I have a really big announcement I want to get to for everybody here. We have our BLT Advanced Computing Summit, Emerging Solutions for Outer Space, Undersea, and Everywhere in Between coming up. It's an all-day in-person event. You get to hear from experts at AMD and from here at LDT on a variety of topics, from SAR on orbit to AI versus PL. It's a really big deal. This doesn't happen very often. And it's so big, in fact, that we're offering it in 4 locations. We've got one here at our headquarters in Columbia, Maryland on April 25th. We'll also be in Melbourne, Florida on May 2nd, Orlando on May 4th, and in Huntsville, Alabama on May 17th. There is a nominal fee associated with it, but the ticket includes hot meals, beverages, a networking reception and parking, and you get to network with the AMD folks as well as us folks at BLT. It is in person, so space is limited. Once the tickets sell out, they're gone. There's no more left. So I will put that link into the chat panel for you. Please check it out. Colton, I am going to go ahead and kick it back over to you in case there's any more questions coming in.
Oh, thanks. Yeah, it doesn't look like there were any more questions since that last one. So I think we're good.
All right, if we have any more questions, do feel free to put those in the chat panel for Colton to answer. Otherwise, we really appreciate you all joining us today for the HLS webinar. And Colton, thank you for sharing all of your expertise with us.
Yep, no problem.